value from Solana.
It's so much more concise.
Okay, everyone, let's go ahead and get started today. Welcome to, this is lecture 13 of 5828, Foundations of Software Engineering. So as many of you are aware, the department's website went down last night, yesterday afternoon about 5 o'clock, and has been down ever since. And so that caught some people by surprise since homework 3 was due today, and you could no longer access the problem statement. So, so I'm extending homework 3's due date from today to Thursday's lecture at 12:30. And I also fell back to putting up the homework assignments, the problem statements, and the lectures up on GitHub. So I sent you all an email about this morning, but you can now go to GitHub if the research website goes down again, and you can access all the slides now. So in this lecture's one, there's all the PDFs here for the slides, because some people were done with the homework but couldn't access the slides and wanted to use the slides to have reference to some of the terms that I'd used. And then there's also one for the homework assignments here as well. And you can go here and click on homework 3, and then the problem statement for homework 3 is available on that page. So if you need access to the homework 3 problem statement, it's now available up here on GitHub, and I sent you that email, that link today. So as a result, I'm not going to talk about the homework today unless there are questions that people have about problems they're encountering. I'm happy to take those. Nope, okay. And then just as a reminder, I have to, because I'm going to be gone next week, I'm doing extra lectures this week. So I did one lecture this morning at 9:30. That was next Tuesday's lecture, which was lecture 15. And then on Thursday, lecture 16, which is the midterm review, will be at 9:30 on that extra lecture slot, and then our regular lecture, lecture 14, will be on Thursday as normal. Now, if you can't come to the 9:30 sessions, it's okay. All those lectures are being captured. I was over in the middle studio this morning, and it'll be made available on D2L. So just go to the D2L website, click on 5828, and then there should be a button there that says lectures or something at the top, and then you can gain access that way. And if you actually come to class next week, like if you forget and you show up to an empty classroom, I believe Kate actually just puts it on and lets the lecture run. So you can watch the lecture here next week if you show up. And I'll send a reminder that I'm not here as well. Okay, so any questions on that? So I had made some mention that I might have tried to squeeze in one more homework between now and the midterm. I've decided against that. What I'm going to do instead is roll out a quiz pretty soon for you to take, which will help you prepare for the midterm. So that'll be coming up. Look for an announcement on email for that. And then the homework assignment that I was going to try to squeeze in, I'll put and have that be right after the midterm. Yes?
What's the format of the midterm?
So the midterm's going to be closed notes, and then it can be questions like we've seen in the homework, short answers, some questions about definitions, so Fred Brooks, no silver bullet, questions, define complexity or conformity, those kinds of things. I typically have a couple of questions that show code and then ask questions about the code in terms of race conditions, or how would you fix this, or what does this Clojure code do, that kind of thing. Now, we haven't had a chance to really apply Clojure in a homework situation yet, so on the midterm, what I might do instead is cover some of the material from the Clojure slides, things that I've covered in lecture, maybe some very simple code that if you were paying attention in lecture or reviewed the slides, you'd be able to answer, but nothing complex until I can get a chance for you to actually work through a significant Clojure program on your own in the homework assignment.
But are they multiple choice? Or?
They won't be, they're typically not multiple choice. It'll be short answer or write some code, that kind of thing. And that'll be coming up on Tuesday of week 9. So this is currently week 7. I'm gone week 8. When I come back, we'll have the midterm. Okay, so today our lecture was to look at some more Clojure concurrency constructs. This is building off of the two lectures we finished last week for functional programming and concurrency. In that lecture, our textbook was just talking about concurrency and functional programming in general. And in this chapter, chapter 4, and some of chapter 3, he focuses in on Clojure, constructs of Clojure that do concurrent programming specific to this language. So we'll be looking at some of those now. And I just wanted to mention, we have one observer today in our classroom. So Mark Gross is in the back here. He's here to review my teaching. And he's the director of the Atlas Institute. He does really cool stuff with robotics and all sorts of fun things. And he asked for a session at the end of class to talk to you. So I'm going to be wrapping up about 15 minutes early today and heading out so he has a chance to speak with you guys. Okay, so that's the lecture for today. And so to orient yourself in the textbook, this is coming in a material that's the reducers, futures, and promises are all discussed as part of the chapter 3, day 2 and day 3 of that chapter. And then I'll be talking a little bit about one of the types of variables that Clojure has to round that out, and that's at the very beginning of chapter 4. And on this topic of reducers that I'm going to talk about next, I point you to a link to a blog post that tries to describe it in more detail. You can follow that link if you need to. That's just some supplemental information. Okay. So reducers is, as we saw last week, one of the things you can do in Clojure or functional programs is code up a single-threaded solution first, and then typically be able to go in and swap out a couple functions and suddenly have a parallelized version. So you take a version of the map function that is normally just single-threaded and swap it with pmap, and suddenly it tries to do things in parallel. The reducers library is basically Clojure's attempt to do this in a very comprehensive manner and give you a bunch of different functions that can all be applied in a lazy manner. But when it's invoked, to actually have everything run as parallel as possible. And so what happens here is that they create a sequence, a set of functions that once you've told what you want to do, give it the input in that, it returns not the result, but it returns instead basically an acknowledgement that you've asked me to do this to a particular collection. So what they call that is a reducible. And you chain a bunch of these reducibles together, and Clojure is able to keep track of everything you want to do to the input collection. Then at the very end, you say reduce, and then because it's analyzed all the requests you've made, it tries to do the minimal amount of work in an optimal fashion, and then parallelizes what it does have to do to try to reduce the collection in as efficient a way as possible. So we're going to make all this kind of more real by just showing you a couple examples in just a minute. So this slide here kind of tries to step you through that. So basically, each reducer allows you to specify an operation that you can build up in a sequence. And all the operations are, as the operations are applied, no work is performed. Instead, it's considered a transformation function. You start with a collection, and then you transform it, and you transform that, and you transform that. And each time, it's just taking note of the transformations you've asked to do. Finally, if you do a reduce or fold on that collection, it then optimizes the reducing function. And I'll talk about what that means in just a minute, and then tries to perform that operation with as much parallelism as possible. Now, you don't get this for free. It only applies in certain conditions. And so here's an example of the type of thing I'd want you to know for the midterm. So if you're taking notes, I would highlight this slide, and in particular this last bullet. So the reducers library says up front, it is best used when your source data can be generated and held in memory. So we don't want lazy sequences. You have to bring the whole collection into memory. And the work to be performed is compute bound, not I/O bound. So I/O bound is lots of reading and writing of disk or reading network sockets or the like. Here, hopefully your task is just computation. You're crunching numbers, transforming strings, whatever it is. And finally, the amount of data is large. So if you can meet all three of those constraints, then the reducers library basically says, this is our milieu, this is where we shine, and we'll give you as much parallelism as we can and be as much faster than single-threaded versions or hand-developed versions are. And so we're going to see some examples of that in just a minute. So just to let you know, there's a wide range of reducer functions that all act in this way, and so we have a traditional version of a map. We have a map cat, which just basically tries to, basically it's their version of basically it's a combination. So they have two functions here, map and flatten. Flatten takes a sequence of sequences and turns it into just a single sequence, where all the subsequences have been emptied and put into a single sequence. So map and flatten, you can do a map which produces a sequence of sequences, and then flatten, and that'll expand it out. Mapcat basically does those two things in one operation. It's like a flat map if you're familiar with that in other contexts. You can have your filter operation, removing operations where you're taking things out of a collection. You can do a take while, which is basically, here's this sequence of things, and I want you to take elements as long as a certain predicate is true of each element. As soon as it's false, stop. And so what this does is it gives you a lot of expression. You can take a bunch of existing algorithms that you might have written in a single-threaded way and see, oh, here's my take statement. I replace that with take while. Here's my flat map statement. I can replace that with mapcat. And you basically have a way to map your single-threaded use onto to this reduce or use. And then finally, you're going to invoke either reduce or fold. And reduce, that's going to kick in the parallel processing. And basically, here's what it does. It takes the underlying data set and groups them into groups of 512 elements each. And it forms a tree structure in memory, a DAG structure in memory that says, apply these functions first, then apply these, then apply these, going all the way up a tree structure to the root. And once you get to the root and have applied it there, you're done with the processing. And it will apply reduce to each of those groups in that way. And what it does is behind the scenes, it uses something in the Java framework called the fork join threading pool. And basically that is an executor framework. So we saw the executor service a couple lectures ago. And the fork join framework, basically what that does is it tries to figure out, did I give a task to a thread that's now blocked so that that thread's not making any progress? What the fork join framework can do is it can take that task off the thread and put other ones there, and just remember that this task has to eventually go back onto the thread. And so what the fork join framework does is it tries to parallelize work as much as possible, and if some task in between gets blocked, it pulls that off and lets other tasks go, and then can put it back on when that task is ready to go. And so the fork join framework is actually the one that is the best performed thread pool in the Java framework. And so Clojure is using that under the scenes for you automatically. All you do is write your Lisp code, and that stuff gets invoked automatically for you underneath. All right, so let's look at some examples. So to bring the reducers framework in to your Clojure program, you have to use the require statement and say Clojure core reducers, and you can alias that library as R in this case. So when we say r/map, that R stands for Clojure core reducers. And here you can see we're taking a function, in this case a partially applied function, partial times 2, and you got a collection 1, 2, 3, 4, and we're going to call our map on it. And the key thing to realize is that when you do this, no work actually happens. So if we bring up a little REPL environment here, oh, and I've got to copy this one first. So once the REPL is up, here I'm doing a require statement. So now my reducers is available via that R symbol. But the important thing to realize is that if I call this r/map, you would think that that would say go ahead and do the work. But as I mentioned, it doesn't. What it does is it returns this weird thing that is basically a Java println statement on, or toString statement on the underlying Java class. But basically it's saying this is an instance of Clojure core reducers folder reify, some weird instance there. So the name is meaningless. But basically it's showing you that when you call this, it doesn't actually do any work. It just takes note. Oh, you have this input collection 1, 2, 3, 4, and you want to eventually map this to be multiplying all those numbers by 2. And then if I go ahead and do another one, some other call on that collection, if I say filter and filter only for evens, again no work is performed, but it just says, okay, so after I multiply by 2, I look for even numbers and I pass those through. And it's only when I call reduce that I will have all those things happen. Right? And what it tries to do is figure out, is there any way I can skip? Like, if anywhere in the chain of calls you called take, for instance, and said, just take the first 10 elements of this sequence, it can use that knowledge to know I only need the first 10 elements of the input collection, and I'm just going to do my transformations on those 10. It could be a million long element, but I won't look at the other million elements. I'll just do the first 10 and stop. Right? So that's what it tries to do by analyzing the function. All right, and then, so here is another example of that. So we're going to call into here, and that is a call that underneath the covers calls reduce. And so this will actually make something happen. And this stream of code here says take, in this case I think that's 10 million or 1 million, take a range of 1 million numbers, 0 to 999,999. And then we're going to filter it to just get the even numbers of that sequence. And then we're going to add 1 to all those numbers. Okay? And then we're going to, that's what the map is going to do for us. And then we're going to pull that into a collection. So now this is going to call reduce in the background. And when it's doing this reducing function, it's going to set it up to only let even numbers through and then to add 1 to all such numbers. It's just optimized to ignore the odd numbers right from the get-go. So if I call this real quick. Now this does not meet all of our criteria in the fact that that range is a lazy sequence, so it's not in memory when we start. I just want to paste it. So this does not meet those 3 criteria, so we're not going to expect to see crazy parallelism here. For one thing, this sequence is a lazy sequence, and so it's going to be generating those numbers on demand. This is certainly not compute bound. You know, checking something if it's even and adding 1 to it doesn't take much work to do. And what was the third one? The third one was the data set should be large. And this is just 1 million numbers. It's not large. So I hit return here, and I forgot the initial parentheses. Sorry. Right there. Maybe it's, okay. I missed a print here. Let's try this. Hopefully, and does that work? So let's see, where's that one? That goes there. That one goes there. Okay, there we go. All right, and then, boom, right? See, it's already generating numbers, and it'll eventually get up to the 999,000 range. And that's going to be, we're seeing only odd numbers here because it let even numbers through and then added 1 to them. So eventually it gets up to 999,000. Now, that wasn't great speed or anything impressive, and primarily because when I hit return, it says calculate this and display it. And so it's displaying the result, and it's pulling in the numbers, the lazy sequence numbers, as they are as they're being generated, as they're being printed. Okay, but so let's go ahead and take a look at an example that will actually show. Oh, right, now I wanted to show this one here. I took that same thing, and I went up to 10 million numbers and ran it. I was just curious to see what sort of CPU performance we might see. And so this is the same operation here. Our fold cat we'll call reduce and kick things off. And the answer was I didn't see much in the way of CPU utilization. It was 100% CPU utilization to generate that calculation. And the reason is that because we didn't meet all 3 preconditions. As I was saying, this here is a lazy sequence, so it's not even starting in memory, which is one of the conditions it wants, and even and increment don't take very long to do, so it wasn't compute bound. So this is something we would expect, is that it wouldn't be all that performant in terms of concurrency. All right, and then just to warn you ahead of time, at this point, the book does something which I didn't think was all that useful. It tries to actually implement the reducers framework from scratch. And there's a big, long section on that, and I recommend just skipping that section. Not worth it. It gets too down into the details for what I'm trying to do, which is to say you can write your code in a single-threaded fashion, drop in some of these functions, and boom, you get concurrency for free. So instead, what I decided to do was to just show you a significant example, which is to count prime numbers, which is compute bound. And we'll count a lot of prime numbers, and that'll give us the large data set. And we'll make sure that we keep it in memory, and then we can see what types of speed-ups we get. Because basically what we want to do is to see an example. Is it worth it? Can I write my programs in this way? Do I see performance that's worth all this effort, right? So, okay, so what we have to do is make sure that we never create a lazy sequence, because reducers need all their collections in memory. And as a result, we'll give a generous amount of memory to the JVM, the underlying JVM, which I think I do 4 gigabytes or 6 gigabytes of memory here. And our program's going to be designed in the following way. We're going to create a collection that contains the numbers from 1 to n. We will apply a map to this function using a function called prime. Basically, the prime function is going to say, are you prime? And we'll get back a true or a false. So when we're done with that map, we're going to have a big long array that says false, 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 true, false, false, right? For true only if it's a prime number, false otherwise. So then we're going to do another map that maps true to 1 and false to 0. And then we can do a reduce that says count up the number of ones, and that will tell us how many prime numbers there were. Does that make sense? Okay, so let's go ahead and see first the single-threaded version. Now, all credit, I borrowed this prime function from a man named Daniel Gruziskic, I guess. And he did the hard work of developing a version of prime that's as fast as the corresponding heavily optimized Java code. You can go to this URL for details on that. I'll just briefly show the thing. It's not really our focus here, so I won't spend too much time on it. But this basically is looking at, asking, is the number n prime? And so what it does is it calculates the square root of prime and stores that in a variable called square root. And then it checks, is n less than 2? Then we will return false. Does it equal 2? We'll return true. And if it's even, we'll return false. And those basically optimize a lot of checks on whether the number is prime or not. And so now, if all of those things don't apply, then what we have to do is check to see if this is just one way of checking prime, is to go up from, if you have 1 to n, go up to about the square root, and then check to see if it's a multiple. And if it's a multiple, it's not going to be prime. There's something in between that actually eventually hits the number. If we get up to the square root and we haven't discovered a multiple, the number's prime. And so that's what this code does. And right now, since it's not our focus, I'm not going to go into detail. If you have questions about this, it uses a loop, and it uses our recur statement that we talked about before. If you have questions about this, let me know via email, and I can help you unpack what's going on here. But regardless, this will tell us. I give it a number, and it'll tell me if it's prime or not. And as you can see also, because it uses the loop here, it's not doing recursion, so I can give it very large numbers, and it will just do a tail call recursion optimization, and it'll just be a true loop, looping through the numbers, even though it looks like it might be a recursive call. It's not treated as a recursive call. Okay, so here's our single-threaded version of this. So we're going to build this up, and the trick is, of course, to make sure that no lazy sequences are created anywhere. And that's because if at any point you create a lazy sequence in a sequence of calls, all subsequent transformations become lazy. And so you'll have lost the lazy nature, the fact that you're trying to make sure that the sequence is not lazy. And all that means is we're just evaluating the sequence and bringing it into memory. So our program is just going to consist of the functions that correspond to that workflow that I had here on slide 9, this one. Create the collection, apply this map with prime, convert to 1 and 0, and reduce. It's just going to a one-to-one correspondence of all of those functions. So here's how we're going to create the collection. We pass in a number n. That goes into range, which does 0 to n. But then we call into, which forces it to realize the sequence, right? Because range creates a lazy sequence, but by calling into, we're saying put all of the elements in that sequence into this vector here. So when we come out of this, we actually have a sequence of numbers that are in memory. Okay? So now we call find primes, and find primes is just going to be a simple map. We're going to call map here, pass in prime, and here's our collection of numbers that comes into this function. Now, if we had just left it at that and passed back the result of map, right then it would have become lazy, right? Because maps return lazy sequences. So what we had to do is call do all, and that forces map to apply all the calculations so that when we're at the end, what gets back is a sequence in memory, and in this case, it'll either be true or false, true, false, true, false, all the way through all the numbers. And so this is where I say here, by using do all, we're insisting, don't use a lazy sequence, fully realize it and put it into memory. Okay, so now we just have to convert to numbers. So again, we're going to use a map function, and we're just going to use an anonymous function here. It takes in a number, or in this case, actually, it's going to take in true or false as the variable, and it's going to check, is this true? If it's true, I'm going to return a 1, and if it's false, I'm going to return a 0. Okay? And then here's our input collection coming in. So this takes a big long sequence of true, false, and returns back a sequence of ones and zeros. And so then the final function here, sum, is just a normal reduce, right? Pass in a plus, pass in the numbers, add these numbers up. Okay, and so and we can just use the single-threaded version of reduce. And so to put all this together, our count primes function is to give us the top number, what's the top number of the range, and pass that in. And the first thing we do is call produce range. That brings that sequence into memory. Then we find primes. This is where all the calculations occur, that big loop thing that I just showed you. Then convert to numbers. That won't take very long. And then we sum them up. And that also won't take very long. So all the work is happening in this stage, where we check to see, is this number find prime? And of course, the prime detection works very quickly on all the small numbers, right? So we have to give it numbers like 10 million, 100 million. And then it's going to, once it finishes 999,999, that takes several loops to go to the square root of that. It's then got to do all that work again to do 1 million, and then all that work again to do 1,000,001, 1,000,002, right? So it keeps doing all that work every time, and that's where we get the compute-bound nature of this process. Okay, so here's the single-threaded performance. The number of primes is from 1 to 10 million. Turns out there's 664,579 of them. And this code, single-threaded code, takes about 6.4 seconds, and it maxes out 1 core, because it's a single-threaded implementation of this. And from 1 to 100 million, there's 5.7 million primes from 1 to 100 million. And all we have to do is just call this again and change the top number here. And it turns out, on the activity monitor on the Mac, you can ask, how much memory is a particular process consuming. And towards the end there was consuming about 6.67 gigabytes of memory to hold all those numbers and all those sequences in memory at the time. And it averaged about 2.3 minutes, again, about 100% CPU utilization. And just as a reminder, I'm not going to run this because I don't have the 2 minutes to spare in this lecture, but I released all the example source code in a GitHub repository, and I point to that from the website. And in that is in the top level, there's a folder here for Lecture 13. And in Lecture 13, if you go down one level, there's a directory here called primes. And this is where all that code is hiding. So if you're in the primes subdirectory, you can open up source primes core. And in that file is, first there's the stolen but acknowledged prime function. And then all of the code I'm showing here. I'm about to discuss the parallel versions in just a second, but basically all the rest of the code is right there. And so what you can do is in that subdirectory primes, you can type line REPL. And when line again brings up your REPL, all of those functions are available at the command line. So it reads those in automatically. So I can say count primes and do a tab, and it knows the function is there. And I can say, how many primes are there in the first 10 numbers, and it comes back and says there's 4 primes, right? So you can launch line a REPL in that directory and have access to all these functions, so you can try them out yourself. Okay, so what do we do to parallelize this? We now have the single-threaded version, and those numbers map out. So now we want to make it parallel. And so what we're going to do here is convert this using the reducers. And produce range is going to stay the same. We still want the collection to be in memory. Find primes becomes just a drop-in replacement. Map goes to r/map. That's all we have to do. So every place that we have in our algorithm where there's a map routine, we just change it to r/map. So there's that one. And then convert to numbers, again, r/map. And then all we need to do is the reducer's version of reduce. In this case, because we're doing a sum, fold is just slightly, I guess, fold would allow us to do an initial value if we wanted to. But this basically invokes the reduce and uses the plus number. So it's right here on r/fold that causes everything to spring to life, create the collection, do all the calculations, and return the result. Okay, so these first two here are producing reducibles. Those eventually get passed in via this collection, and the third performs the entire operation in parallel. So what do we see on the performance here? The parallel version then is just updated, so count primes parallel. Produce range stayed the same. Find primes just becomes find primes parallel. convert to numbers parallel, and sum parallel. Okay, so we're just swapping functions to get the parallel version. So performance, the number of primes, again, the numbers, matched up. But what was funny about the 10 million example was that it took about 2.5 seconds to do. And it was so fast that on top, the program barely appears, so I couldn't see how much CPU utilization was going on in that case. It was too fast to see. But if you recall, the single-threaded version was about 6 seconds, so it's 3 times faster, and all we did was swap map for RMAP. And we had to make sure that we weren't using lazy sequences, but then everything else happens in parallel. And the number of primes from 1 to 100 million took about 35 seconds. I saw as high as 790% CPU utilization. This machine has 8 cores, and when you have compute-bound processes, you want to have basically one thread per core. So it was basically maxing out all cores, and ended up being 3 times faster. And actually, the amount of memory that was consumed was actually smaller, because what's happening here, in the single-threaded version, we first bring in a 100 million element array, and we fill with numbers, and then we create another 100 million element array, which have the true-false values in it. And then finally, we create a third 100 million element array in memory. So all 3 of these things are in memory with zeros and ones. And then we reduce that. On this one, because the reducibles are saying, hey, first convert it this way, and then convert it this way, and then add this, it actually can avoid having to create those 3 collections. And each time it gets an element, it applies all of the operations at once. It does the prime, it converts it to true, and converts it to 0 or 1, as it's processing each element in parallel, broken up into those 512 batch group sizes, and then throwing that out across all the cores to be as fast as possible. And what's nice is that we never had to say new thread, we never had to implement runnable, we never had to worry about race conditions. All of it goes away from just having to swap map to RMAP, right? And so this is where these frameworks, they definitely come at a cost. I consider having to learn Clojure a cost. I've been in the non-Lisp world for so long that it takes a while to learn these things. But you can see, after having worked on homework 3 for many of you, and seeing how insidious race conditions are, like I've got people who say, oh, I finally got it to work, but I have no idea why it was not working, and I was glad that this was working, that kind of thing. Or I even had one person who was like almost there, and so 9 times out of 10, they would run it and they get the correct output, then they'd run it that 10th time and there would be incorrect output, and they'd just be like, throw their hands up, right? So we're trying to get away from having to deal with that insanity and make it so that we can actually reason about the programs that we're making in concurrency. All right, so any questions on that? And the way I presented this is the way I would like you to engage with it. Go into that directory in the example code, bring up line REPL, and then type, put some input into each one of those things and see what comes back out. Play with it a little bit. But if you understand the single-threaded version, all we've done is said to Clojure, just please make this parallel for me automatically. And behind the scenes, it's going to try to maximize the amount of resources that it has on that machine to calculate as quickly as possible. Okay, so now one of the problems, however, oh, yes?
Sorry, is there any way to modify the behavior of the reducers?
So modify in what way?
Well, limit it to thread count, or give
Okay.
it
All right, ask it, could you please use 16 cores, not 8 cores, or those kind of things. So the answer on that is no, because what it's trying to do, the framework itself knows that it's compute bound. So that's what it's meant to do. So it's only going to ever allocate a thread pool that's going to maximize that scenario. So you're going to get 8 threads on a machine with 8 cores, or you're going to get n threads with n cores, right? You definitely want to be able to give Clojure more memory, and you do that outside of the framework. When you're launching it, you tell it, and I think I gave an example in the very first Clojure lecture, which basically says, hey, for this Java VM environment variable, crank it up to 4 gigabytes, 6 gigabytes there. So that's what you can do there. So no, so what, actually it's a very good point. So can I tweak it? The answer is no, and that's because what they're doing is they're not trying to be a generic concurrency framework that handles all concurrency. They're identifying up front their sweet spot, compute bound, in memory, lots of data. And if you meet all three of those criteria, they're like, we can make it very easy for you to maximize your course on that. But if you've got I/O bound work, you can't use that framework. Right? If you're going to be calling sockets, do not use reducers. It's just not, it just wasn't built that way. Like Ruby on Rails is great for database-backed websites, but if you, as soon as you want to say, hey, I don't want a database, actually, I just want to, it's like, okay, well, go use something else. We're optimized for relational databases and that kind of thing. So that's what's happening there. Okay. So now we're going to leave behind reducers. I just want to kind of say this is what it does, and it's very good at what it does in that particular domain. And now we're going to look at some other kind of concurrency constructs that Clojure offers. And the two other that the book talked about at the end of chapter 3 is called futures and promises. And futures, what you do is you declare, here's a block of code that I want to run in another thread. And I'm going to hand it to you, and I want you to give me back a variable that I can ask what was the result of this code. So assume in general that the code you hand off to this future is something that's computing a result. And at some point I'm going to go back to it and say, hey, what was the result? So what's nice about a future is that it's kind of this little fire and forget kind of thing. At the start of my program, if I wanted to, I could generate a bunch of requests to futures with code that needs to be calculated and let that all just run in parallel beyond my main program. And then eventually I can get around to saying, oh, hey, those things I asked you to do, what are the results? And then I can loop through them and say, give me the result for future 1, future 2, future 3, future 4. And what is nice about this is that if you call and say, hey, what was the result? And the thread that's associated with that future is not yet finished, your main program blocks. So you synchronize on that call, and you wait until that thread is then done. You're doing a thread.join, essentially. Once it's done, you get the result back immediately, and then you can go on and do work again in the main thread, which in these programs typically is call the next future and say, hey, do you have a result? And what's nice about this is if you launch off a bunch of these things, like 100 of these futures, 1,000 of these futures, and then your main program is just a loop that goes and says, what was the result, what was the result, what was the result, and does some combination on that. What will happen is your first couple of calls will block as the threads are still getting their work done. But while you're blocking on those, the other 999 threads are finishing their work in parallel. And at some point, your calls to those, what's the value, return immediately. And you're getting really fast performance because all the work's done. It was all done while you were blocked on the first couple. And so this can be a great way of parallelizing work with a very simple main routine. The main routine comes up, fires off all these futures, and then just loops over each one, waiting for the results to come back. Okay. So the code looks like this. Here's a def sum, so we're creating a new symbol. And that sum gets not the result of this code over here. What you can see over here is that we're adding the numbers 1 through 10. But we wrapped this call to plus 1 through 10 in a future. And so what comes back from this is not the result, but the future object that I now have a handle to. So if I want to show this to you real quick, in the same way that the reducible didn't return a result, the future doesn't return the answer, it returns back an instance of future. Right? Now that code is already run off. I don't have a handle to that future object. I can't actually resolve that one. And that's why with these futures, what you're doing is usually creating an array of futures so that the array holds on to the future handle so you can then go back and ask for it. So if I do this, now I get a handle called sum. If I do sum and just do a return on this, I get back the same thing. This tells me sum is a future object, is what that's telling me. So to get back the value, I have to deref the future. So in this case, I have to say, hey, I want to dereference you. What was the value? Right? Now, if it took a long time to add 1 through 10, which would mean something's wrong with my machine, this return here would cause me to block. But now what will come back is, oh yeah, it's 55. We calculated it eons ago in computer time. But now finally I have it. Another way of referencing that number that's shorter is to just say @sum. So now if I say add sum, I get 55, and it goes there, and it comes back. So once the thread is finished, this just acts like a symbol that has a value. You just have to remember to dereference it. Okay, so that's what this slide said. Oh, yes?
So if you go back to the REPL,
Yeah.
the sum, it looks like it calculated the value, 55.
Yep.
When you said future. So it actually is calculating it? Or
Let's see. Oh, yeah, that just means that when it returned back, it calculated it so fast it already had the value by the time the REPL went to print. But this is showing the status. So let's say it was a really long-running thread, then that status would have been different. It just, in the time that I hit return and before it could print out the result, it had already finished the calculation. Yeah. Yes?
Can you instead check for the status in a non-blocking structure?
I believe so, but I would have to go look. I don't know that off the top of my head. But yeah, there might be ways of asking the future other things. But basically what you want to do is this fire forget mode. Here's all these things I want to happen in parallel. Go do them. I don't care how you get them done. And this is where you can use futures for I/O-bound work, right? So you can say the function that I'm passing you to the future is going to go hit a web service, and it's going to wait the eons of time that the web service takes to bring back a result. And when I'm finally ready to go display the results of that, I will block on that future and wait for the result to come back from the web service. Okay, so I'm going to keep going, but there are other examples I'll put in the sample code that shows futures being used. And I'm actually working up to one such example that uses something called atoms in just a minute. So even though this was just, basically I'm just providing an overview here, the example will come in just a minute. The other thing that the book talked about is promises. And a promise acts like a future. You can create a promise, you'll get back a promise object. And then at some point you say, hey, promise object, what is your value? And if you do that and there's no value to be had, you block. And so if you get back a promise, if someone hands you a promise, as soon as you decide to take the plunge and say, hey, what's your value, your thread blocks. And what the difference between the future object and the promise object is that some other thread also has a handle to the promise, and it's going to call a function called deliver. So it's suddenly found the value that needs to be delivered to the person or the thread that's blocked on the promise. And so it gets that value and calls, hey, deliver to this promise this value. And now the other thread that was blocked unblocks and gets that value. So it's a way of doing communication between multiple threads. Right? If you create a couple of threads and share the same promise between those threads, you can say, oh, I need to pass this information. The number I computed was 25 to the master thread. So what I'll do is I've got a promise that I know the master thread has. I will tell my promise, hey, 25. And now, meanwhile, the master thread is looping, and it every now and then checks and says, oh, I wonder if one of my threads is done. I'll go to dereference this promise, and oh, yeah, it's done. I got a 25. And it comes back that way. And so this way you can communicate safely values across threads, and it'll be visible, right? So we won't have any race conditions or memory visibility conditions. It'll be synchronous. I'll block until the value's there. So you avoid a bunch of the race condition stuff that can happen in Java. Okay, so let's see an example of this. To create a promise, all you do is call the function promise, and you immediately stick it into a symbol. Oh, yes, question?
Does the deliver multicast, or does it do only one instance of the promise?
Multiplex across multiple promises? Is that the question? Or
If you say deliver this promise, but the promise is shared among multiple threads, would all threads get it?
yeah, so if any thread that has that promise dereferences it, and you've already delivered the value, it just gets the value. Yeah. Okay, so here we're creating a promise called the meaning of life, and then we're going to create a future that blocks on this promise. So I'm creating a future, and the task of that future is to do print line. And in the print line statement, we say the meaning of life is, and here we dereference the promise at meaning of life. So what that means is that as soon as we type future there, another thread spun up called print line was trying to do it and blocked on meaning of life. So this is code you can run in the REPL, actually. So let's do that. If I go like this and copy this, do paste. So we've created our promise. And if we, first of all, let me just show you. If I do future, print line, hello world, that, hit return, hello world's going to be printing out immediately. Now, this happened in another thread, not the REPL thread, but it created a thread. That thread said hello world. It printed out to our screen because they share the same standard out, and then our REPL came back. But here, I'm going to paste that code. Here I'm doing the same thing, calling print line, but I'm dereferencing the promise. And now when I do that, you can see that we get back this promise object notation, but nothing printed out. All right, so there was no corresponding hello world or anything like that. We want to see the meaning of life, but it's blocked. That other thread is blocked, waiting for a promise to be delivered, and that's what you do here. You call deliver, you pass in the promise, you pass in the value. And when I paste this, immediately the meaning of life is 42 finally can print out. Right? So I delivered 42, the thing that was waiting for 42 unblocked, and it could finally do its print statement. And so you can get this becomes a very lightweight and very easy way to pass things between threads. It's one of those things that in Java programming comes up a lot. I've got these producer threads over here, these consumer threads over here. As you saw in our homework, we used a queue to communicate between them, right? Then we had synchronous you add synchronous locks eventually to make sure that those values get communicated. But sometimes it's not clear. How do I get this value over to the other thread in a safe way? And this is one way of doing that. Okay, so what and let me just keep track of time here. I've got 15 more minutes before I turn it over to Mark. And anything that I don't finish today, I'll just let spill over to Thursday. And I've got a somewhat shorter lecture on Thursday, so we'll have time to finish up there if we need to. So to combine the use of future and promise and deliver in a meaningful application, the book creates this thing called the Simple Web App. And it's a snippet handler where basically you have a web app that wants to print out snippets that it receives. But it's only going to print out snippets in order. So you have to say, here's snippet 1, and here's the text, and it'll print that out. Here's snippet 2, and it'll print that out. If you send it snippet 6, it'll remember that you sent it snippet 6, but it won't print it out till it gets 3, 4, 5, and 6. Okay? So that's what the web app does, and what it's expecting is a call to a URL that ends with /snippet/:n. So you can say, here is your snippet N. Here's snippet 4, here's snippet 5, based on the URL. And then you pass it text in the body of the request so that it knows for this snippet, here's the actual text of the snippet. Now, if you want to see this code, go to the code source code directory and cd into the functional programming directory, and then go into transcript handler. That's the name of this particular program. Okay. So the setup, I want to just step through it and I'll show it to you running, is the following. We haven't seen this closure function yet, but it creates a lazy sequence. So if I had the function increment, and I pass to increment 0, normally I would get just 1 back as the result of that. But if I say repeatedly increment 0, that creates a lazy sequence, which is 1, then 2, then 3, then 4, then 5. Repeatedly will just call the function it was given every time the lazy sequence needs a new value. So now what we're doing is something a little bit dastardly. We're saying every time that you get invoked, give me a promise. Okay? And we're going to call that snippets. And then here, in a future, in another part of the web app, we are going to call a map on snippets. Remember, snippets is just a lazy sequence of promises. And what's the function that map is going to apply to every element of that sequence? Deref. So basically, give me my next snippet and block. Right? So the web app just wants to know what the next snippet is. And so what this is going to do is cause it, every time it gets a new snippet, it's going to block on it. As soon as it gets its value, it's going to print it. Right? And so this is the reason why it prints only version 1, then 2, then 3, then 4, because as soon as it's printed out 1, it goes and says, what's the next one, gets it, calls deref, and blocks again on it. Okay, and so then what we can do in our other code, the web server, Jetty in this case, is waiting for connections from the clients. It has a bunch of handlers sitting in other threads. From the URL, it finds out what the snippet number is. And once it has a call that has come in from a client, it takes that text and says, I need to deliver. So here's the call to deliver. Based on what the number was on the URL, I need to get the promise object that corresponds to that snippet number. So here, if I've got from my URL, from my client call, I got the number of the snippet plus the text of the snippet. What I need to do is say, get the promise object that is the nth one into the sequence, and then deliver to that one the text. And so now think what's going on here. We've got this lazy sequence of snippets. The web app is going to come up and wants to print the first one. It blocks. It's waiting for snippet 1. At some point, someone calls it with snippet 1, and here's the text. And this code will deliver to that promise the text, which causes the other thread to wake up, get the text, and print it. And then it asks for snippet 2 and blocks again. And so now if I call snippet 6, this function skips ahead in the lazy sequence and says, give me the 6th element. And so what happens in memory is it actually, if I've only done 1 and 2, it will, behind the scenes, create 3, 4, 5, and 6 on demand. So it waits for a demand, creates all those, and then returns back the snippet that's going to be 6. And this then calls deliver. And so that promise is just sitting there waiting to deliver its value, but it won't actually happen until I call 4, 5, and 6. And then when it finally gets to that 6th one, it'll immediately dereference and get the text. All right, so let's see this in action. I need 2 windows this time. I'll make this bigger. And go to 5828, fall 15. Go to the textbook, functional programming, transcript, handler. Okay. So if I remember right, in this I just have to call the main routine. Yes. Okay, so I just say line again, run. And all that code I just stepped you through is in there. I'm not going to go into it in detail now just for the interest of time. But this brings up a web server, and on port, if I remember right, it's port 3000, and now it's waiting. The code that is going to print snippets has asked for the first promise. It wants to print it, so it's going to deref it, and now it's blocked. It's waiting for some other thread to deliver the first snippet. So to do that, the book shows you a curl command you can use to deliver that snippet to the web server. And I put that, I've got to remember where I put that snippet. I think I put it 5828. Where did I put that? Okay, what's it in here? Oh, there it is, snippets.txt. Okay, so here's our snippets. I just have 3 of them. And it takes the Jabberwocky poem, so 'twas brillig and the slithy toves, and that's going to be our snippet 0. Then I'm going to paste in snippet 2, so I'm going to go out of order, and then I'm going to paste in snippet 1. And so what we know of this program, when I do this first one for snippet 0, it'll immediately print it. Then I'm going to send off snippet 2, and we won't see anything happen. Then I'll paste snippet 1, and we'll immediately see 1 and 2 print out, right? Because it'll dereference 2 finally, get its value printed out, go to 3 and discover it's already got its value, and just immediately print it out. So, okay, so here we go. Copy that. We need 1 more. And yeah, that's what I was worried about. I got to get, there's a little space in here. And return. And over here, lo and behold, it says 'twas brillig and the slithy toves. So the web server woke up, printed the snippet, and tried to deref the next one, blocked. So now here I'm just to make it easy, I'm going to keep sending that same that same text. I'll change it just a little bit so we believe that it's being changed. We'll get rid of toves this time. We hit return now. Oops. Oh, the joys of typing in front of people. All right, come back here. What did I do? I got rid of a quote. Okay. So it comes back, nothing happens. Over here, nothing got printed, right? And that's because we delivered to promise 2. We haven't dereferenced that one yet. So finally, we're going to deliver to 1. and it immediately prints out those two. Prints out 1, prints out 2. So you've got this, all of this is happening through promise objects. You have the web app is basically used future to create a separate thread that's printing these out, and it just blocks on promise. And then another part of the web app is waiting for calls like this from curl, taking the text and delivering it to the correct promise, and then you get your transcript in order. So any questions on this? Okay. All right, I have just a few more minutes, and let me just show you the architecture here. This is what I was describing verbally. So what you've got here is the snippet processing thread, and it goes, first handle snippet 1 where it blocks, snippet 2, etc. And then over here you've got the delivers coming in, and no matter what order it comes in, it finds the promise object and delivers to that particular promise. Each of those in a separate thread. Okay. All right, yes?
Can you define a variable normally, like the defn?
Yep.
Is it by default mutable or immutable?
Okay, good question. So in other languages, we say, hey, I'm going to create this variable, I'm going to give it a value, and at some point later, I'll change it. Now in Scala, or Scala, I never know how to pronounce it, you could say val x equals 10, and if so, you're saying, I want this to be immutable. It'll never allow me to change. If I then say x equals 5, it'll complain, hey, you told me this is immutable. If I say var x equals 10, I get a mutable variable like normal. In Clojure, everything's immutable. So you can't, and actually, I just said that, then I'm going to slightly modify it in just a minute, but in the things that we do actually can change, we change in a thread-safe way. So all the things are immutable. So if I say def x 10, x is a symbol that points at 10, and that value 10 will never change. And you can share that freely with all the threads and don't have to worry about it. If it was def x in a big long sequence, that sequence also never will change. It's immutable. So where you can get things that change over time is actually a great segue into what we're talking about as the last thing. So Clojure does have something known as a mutable variable. And they call them either refs, atoms, and agents. Okay? And what it does is it say, okay, yeah, sure. Some programs, we acknowledge, need variables that change over time. So what we're going to do is define the semantics about how that change is going to happen. In other languages, we just let it happen, right? And it doesn't matter if we're in multi-threaded mode or single-threaded mode, we just change it. We just mutate it. In Clojure, we say, yeah, if something's going to change over time, tell me how it changes over time. And so the three different types of mutable variables that it has are refs, atoms, and agents. Agents are used if you've got a variable you want to keep track of. You don't want any race conditions on its values, but you always update it asynchronously. You say, hey, variable, change to 5, please. Okay, now change to 10. I'm not going to check, but just make sure that you do it at some point. And that's what you do. If you have asynchronous updates, you use agents. If you want a value that was previously 5 and now has to be 6, and you don't want any threads to be able to change it while that happens, then you have synchronous updates through atoms. And this is similar to what we saw in homework 3 with the synchronized keyword. So with the synchronized keyword, you can block the change to a variable and make it synchronous so that all threads see the change. But it's uncoordinated in the fact that, let's say you had 2 variables that you wanted to change. Either you use that synchronized block and put your changes in the block, but if you're using synchronized methods, you first update one, and that's done synchronously, and then you update the second one, and that's done synchronously, but the 2 updates together are not coordinated. So it's possible for one thread to change this one while another thread is changing this one. But if you want both of them to be changed at the same time, you can't use synchronized on the methods, and you can't use atoms in Clojure. What you'd have to use is refs. And what refs are for is, I see this parenthesis here, software transactional memory. With refs, you say, here are 4 or 5 variables that I care about. They will change over time. And they're all, when they change, they're all going to change at the same time. And so the only way to do this is to say this is a transaction. I'm going to start the transaction, make my changes, and commit the transaction. As soon as the transaction is done, all of the changes become visible to all threads. But if anything causes any one of those updates to fail, the whole transaction rolls back and no one sees any of the changes. Okay? And so Clojure forces you to say, what are your semantics for your mutability? And then you use the one that you want. Okay? So now what we're going to do, and then behind the scenes, this is all supported using Clojure's persistent data structures, which I definitely won't have the time to discuss today. I'll discuss more on Thursday. But I previously referenced it when I said, if you've got a big, long map, say it's a map with 10,000 entries, with immutability, it just seems crazy to us. If I want to change a value in that map, do I have to copy that map? Right, copy all 10 million entries and then apply the change and then have that be immutable. And if you recall, I mentioned that Clojure doesn't do that naive way of copying. Instead, it says, yeah, you've got this 10 million entry map. You're going to make one change to it. The only thing I do is take note of the change. And then I share everything else from the previous map. And so these persistent data structures make sure that as we're changing things over time, because the values of these variables can actually be these big, complicated data structures, trees, maps, sets, whatever, we'll make sure that as we change those over time, we're using the smallest amount of memory possible to keep track of all the changes that have been asked. All right, so I'm going to have to start here on Thursday describing how you use atoms. And from here, atoms are this one, uncoordinated synchronous update. If that's your semantics for mutability, then that's the one you use for Clojure for this. And we'll discuss this on Thursday and then also do the Agile lecture that's planned for that day. All right, so I'm going to wrap up, and Mark Gross is going to come forward and talk and ask you a few questions. All right, thanks very much. Yeah. Okay. All right, I've got a Clojure convert here.
Cool. So I actually come from functional programming Lisp background, so this was all quite related to my personal interests and yet new, and because I don't know Clojure, so I won't take much of your time because I also have to run. But please bear with me for 10 minutes. My name is Mark Gross. I'm a faculty member in the computer science department. I'm also the director of the Atlas Institute, which, if you don't know, is just up the street, kind of near Norland Library. And I invite you to come and participate in the things we do because you might find them interesting. And I'll also put a flag out for the course that I'm teaching next semester on technology for sport and play. So it's a project class. You build your own stuff. It'll be fun. What I'm doing here is normal. So we're considering Ken for promotion to full professor from associate professor. Some of this stuff may be really familiar to you, some of it may not be. The normal process is to send someone in, the agent like me, into the class to observe his teaching and to collect information from you, the victims, the students, about how he's doing. So that's what I'm here for. I have no axe to grind. I don't know any of you, so you can be completely frank, and I won't know who you are or who said what. My job is to report in a 1 or 2 page letter